In this tutorial, I'm going to be outlining how to use MENOTR to fit a data set described by a line. So here we have the equation y equals mx plus b, which is what we're going to be fitting our data to. We have our independent variable, which is time in this column. We have our measurements of the signal in this column. And in the third column, we have standard deviation measurements for each of those individual signal measurements. So now this file is located within this folder called tutorial1. So if I open up this file, this is the only Excel sheet within this file, the only item within this file. So the first thing to go about this process is to open up the MENOTR master scripts directory. So now within that directory, you're going to see a series of files shown through here. So we have closed form equation, chemical reaction scheme, so on and so forth. Here we're fitting to a simple closed form equation of y equals mx plus b. So that falls into the closed form equation case. So we're going to copy over this whole folder. So we're going to copy, and we're going to copy that from the master scripts directory into our tutorial1 or our working directory. So now that that's located in there, we're going to now copy this location and go into MATLAB. And now if we open up MATLAB, we can just drop in that location shown through here. We can do CLC to close this warning that was displayed previously. Now for you guys, I think it will probably, your MATLAB will be set up into stop grouping. So you'll see something like this. I personally prefer to click on this little tab shown through here and do group by type. And it's going to group all the folders together, all the Excel sheets together, and so on and so forth. So now the next step is to go into that directory, the closed form equation. And now you're going to see a series of different scripts that are present. And now these are going to be grouped by their respective type. So we have folders, functions, and scripts. So now the first thing we need to do is open up the model simulator. So if we open up the model simulator, you're going to see this file looks like this. So now how we've structured these scripts is such that the green is describing what is actually being achieved in that particular portion of the code. And now here I want to point out some key features though. So at the top of each file that you're going to be working with, there should be something that looks like this, where it says sections that require modification. And I'm going to tell you which sections that need to be modified for your specific case. So here that's section 2 and section 3. So this is section 1, section 2, and section 3 shown below. Also, additionally, to help you orient yourself as to which sections require modification, we also mark them with 3 stars. So that's also the section 2 and section 3. So now, if we want to go about actually fitting our data to a line or y equals mx plus b, first thing we need to do is to go down to section 2. And now section 2 is defining the parameter. So what you're doing here is defining your independent variable, which we have as x as our independent variable, and we're going to define the parameters that we're going to be optimizing. So those are m and b. Now we define them as such, where you have params 1 and params 2. Now, if you have additional parameters in your model, you would just define them like so. So if you had a d, for instance, you could have params 3, for instance, but we don't have that here. So now we're just fitting to y equals mx plus b. So we have our m and b, our 2 parameters that we're going to be fitting to. And now in section 3, we're actually defining that equation that we want to fit our experimental data to. So the way we go about doing that is we say that the simulated data colon comma 1 is equal to m times x plus b. So now we're using those parameters that we defined, and we're telling the code how we use those parameters and the independent variable in an equation to describe the data. So now, in this case, this has all been edited to describe this particular model. So now once you put in your edit the step 2 and step 3, you need to save the code. So you just save. Let me make sure I didn't edit anything. Okay. And now the next step is to go into step 1. So now we've customized the model simulator to describe this particular model that we're trying to use to describe our experimental data. So the next goal is to actually use that model in fitting the experimental data. So now how that's achieved is through a series of 3 steps. So the first step is pretty simple. It's just data input. So once again, we have this green text is outlining how what is being achieved in this step or this portion of the code, and some notes and that sort of thing as to what's going on. But suffice to say, all you need to do here is run this script. And now, but one of the things I want to, so if you run the script, it's going to generate a matrix called insert data. And now one of the things I want to bring up is that what you're doing here is you're inserting your data into MENOTR, and it needs to be in a very specific form where you have a matrix where the first column corresponds to your independent variable, your second column corresponds to your first data set, your third column corresponds to standard deviation on each of those individual data points. If you have additional data sets, they go in as shown through here, where you have alternating the first data set, standard deviation, second data set, second standard deviation, third data set, third standard deviation, and so on and so forth. So in this case, we're just fitting one data set though. So we're just going to copy this in such that we have our independent variable, the corresponding dependent variable or the data set 1, and the corresponding standard deviation measurements. So if we copy that over, in that insert data matrix that popped up originally, we can just click and put it in like so. So this is all that needed to be done with step 1. So you're putting the information into insert data, and now you can close this. So insert data shown over here in the workspace has already loaded in those data points that we just loaded. So it has 10 times 3, which is 10 rows and 3 columns. So that's all that needs to be done for step 1. Now for step 2, the broad goal of step 2 is the algorithm setup. So here, once again, we can look at this top section to know which sections need to be edited. So we're going to be needing to edit section 1 and section 2 of the step 2 algorithm setup script. And now the first thing we need to do is go to section 1, which is our parameter guesses, note the 3 stars. And we need to define our initial guess for these parameters. So we have 5 for the M, and we need to define upper and lower bounds for each of the parameters also. So I'm putting an upper bound of 1,000, a lower bound of 0.01. And for B, I have an initial guess of 1, an upper bound of 1,000, and a lower bound of 0.01. The next portion of step 1 is actually just organizing these parameters into these matrices shown through here. So param vals just composes each of your individual parameters. So here we just have 2, which are M and B. Param's upper bound and param's lower bound are just those values that you defined here. So you're going to put M and B, and then M underscore upper bound, B underscore upper bound, M lower bound, and B lower bound. And now to clean up the code, we just type in M and B, each of these terms shown through here, into this clear component. Next, so step 1 is now satisfied. So now if we go to section 2, here we're defining the fit set settings, or the iteration control vector. So the broad idea here is that each cycle is performed, the user is going to define a number of cycles. So here we have cycle 1 and cycle 2. And within the first cycle, we need to know how many times to perform the genetic algorithm. So the genetic algorithm is going to have 3 generations or be performed 3 times, where each optimization is refined multiple times. So we're going to perform that 3 times. We're then going to perform nonlinear squares possibly. So in the first cycle, we're going to perform 3 cycles of the genetic algorithm. And now we need to define which parameters are going to be allowed to float versus which parameters are not floating. So how we define that is by defining a series of 1s and 0s. So here, this is called the cycles matrix. So it's the parameter M, the cycles matrix for it, the parameter M, we have as 1, which says that that parameter M is not float, or rather, that parameter M is allowed to float. Likewise for B, within the cycles matrix, has a value of 1, which says that that value B, the values of B are allowed to float also. Now the parentheses 1 shown here corresponds to what cycle you're working in. So parentheses 1, parentheses 1, parentheses 1, all these correspond to the first cycle. So once again, this is m underscore b. So this is the cycles matrix for parameter m. Within the first cycle, we're allowing that parameter to float. Within the cycle matrix, so we have the parameter b within the cycles matrix. In the first cycle, we're going to allow that parameter to float also. Now getting back to the nonlinear squares, so now we need to tell MENOTR whether we want to perform nonlinear squares or not within the first cycle. By default, we recommend that in the first cycle, you just use strictly the genetic algorithm. And then in the second cycle, you use the genetic algorithm plus nonlinear squares. So here we have nonlinear squares for the first cycle. Do not perform nonlinear squares or 0, which is defining that. So now in the second cycle, we're going to, so that's parentheses 2, we're once again going to have 3 generations of within the genetic algorithm, where then the parameter m within the cycles matrix, within the second cycle, we're going to allow that parameter to float and b also to float. So once again, this is parentheses 2, indicates the second cycle, and the 1 tells the code that that parameter should be allowed to float. Now, nonlinear squares in the second cycle is going to be repeated, or excuse me, is going to be performed after the genetic algorithm. So, and we say that nonlinear squares should be performed by giving a value of 1. So this needs to be performed for each of the parameters within your model. So you would generate a similar value, such as d underscore c of 1 is equal to 1, would be saying that we have that parameter d within the cycles matrix. In the first cycle, we want that parameter to float, and so on and so forth. But we don't have that here, so we don't need that. Okay, likewise before, we need to organize our parameters into this additional field. So the SciMat is just organizing those parameters. So we have m underscore c, semicolon, b underscore c, semicolon, and nonlinear squares. And then we just put into clear m underscore c, b underscore, and nonlinear squares. So you just, whatever parameters you put into this section need to be loaded into SciMat, and then we're going to clear the parameters out once they're loaded into the SciMat. And this is all that needs to be performed for step 2 algorithm setup. So we satisfy the conditions for section 1 and section 2. So now that the step 2 has actually been edited to match our particular model, what we're going to do is we're going to run this code. So now you can run step 2. Now you simply run step 2, and after running step 2, you should see within your workspace a number of different parameters that MENOTR is going to use to perform your fit. So now if we open up step 3, and now step 3 has been set up such that you just have to press run. So step 1 and 2 are heavily edited based upon your particular model, but step 3 is actually executing the MENOTR algorithm, but it's using the instructions that you defined in step 1 and step 2. So you simply just run step 3. So now you'll see in the display shown below that the MATLAB code is setting up the parallel pool. So MENOTR has been designed to run as many calculations in parallel as possible to increase, or rather to decrease, the runtime. Okay, I want to stop this for a second before it gets carried away. Okay, so what you're seeing here is the information pertaining to the first period, the optimization routine once, or the first optimization routine, the first cycle, and the first generation. So recall we defined the number of cycles. We have number of generations as well as the number of cycles. So we said to perform within cycle 1, which is just the genetic algorithm, to perform the genetic algorithm 3 times without nonlinear squares within the first cycle. So here what you can see is we're going through those generations. So we're doing 1, 2, 3, and then the code will kick over into the second cycle and perform this again 1, 2, 3 times. Additionally, this is all being performed in the first optimization routine. So the first optimization routine is composed of 2 cycles, one cycle with just the genetic algorithm, and the second cycle includes the genetic algorithm plus the non-least squares. So once the 3 optimize, so the optimize, this is the results of the first optimization routine. 3 optimization routines are going to be performed, and then the resultant outputs are going to be compared. So here, let's go ahead and do that. So now I'm going to continue running this code. And now what you're seeing here, let's make this bigger. So what you're seeing here is the experimental data, our independent variable or signal. We have our changing chi-square as a function of the iteration number. And we have that LSQ non-linear is turned on. The best fit parameters are 20 and 1.623 at the moment. We have some additional information over here where we have the best chi-square. We're in the first period, we're on the second cycle of 2. We're on the second generation, and we remember we defined that we performed this 3 times. We have the Armistice invariance. So now let's go ahead and continue. Okay, so now after those 3 optimization routines are performed, so as you can see, 1, 2, 3, the resultant chi-square are shown through here. So they're pulled together, and now this describes the first period. And now a series of comparisons are executed where the code asks, is there a significant difference between these 3 different chi-square values? Additionally, is there a significant difference between the parameter values which were generated from each of these individual fits or these optimization routines? So here the answer is no. As you can see, the relative standard deviation of the period parameters was incredibly small, and also the difference between these chi-square values was very small. So thus the code stopped and reports that's done. And this took 2.5 minutes because I'm pausing it throughout. Now, if one of these chi-square was larger than the other 2, it would have given rise to a difference between the different optimization routines. And so the best of the optimization routines would have been used as the starting guess for another set of optimization routines. And that kicks over into the second period. So this is performed iteratively until all 3 resultant outputs are identical. And now after the fit is complete, we can go over here to the right and get the fit chi-square, which is 0.26. We have the fit parameters, which are 20 and about 1.6. So this is that M and B. So our slope was 20, our y-intercept was 1.6. We can generate, so here, let's pull this up first. We have a plot, oops. Let's open this outside of MATLAB. So we have a plot of the experimental data with the best fit line and a plot of the residuals. And now the actual data points for the best fit line, and the residual plot are shown here, where we have the fit residuals shown here. And we have the simulated data, or the best fit line is shown through here with the corresponding experimental data. So here we figured out using MENOTR. Oh, I need to say this too. So we can open up that figure shown through here by going back into this folder, which is the final plot.tiff. Additionally, MENOTR saves the workspace over here into fit_workspace. So in the event that you clear this out or delete it from your working directory, oops, suppose now you wanted to know what those fit parameters are, but you've closed it out. So you can retrieve those by just clicking over here into fit workspace. And now all this information is shown to the right. Now for some reason, if you want additional information, you can click over here into the complete fit workspace and all the individual fitting parameters are listed, but that can be a little daunting. So we organized, we organized the ones that would be of immediate interest into just this fit workspace for you guys. So now in this tutorial, I've shown how to go about fitting a data set to a line, and we've figured out that our fit parameters are 1.6 and 1.2 to describe this experimental data. This is our value for M and B for this experimental data set.